Apollo missions. For instance, during the first moon landing in 1969, Neil Armstrong and Buzz Aldrin spent just 2.5 hours moonwalking, and the farthest they moved from their lunar module was 200 feet by contrast. However, in the final Apollo moon mission, Apollo 17, in 1972, the crew of two, Eugene Cernan and Harrison Schmitt, spent more than 22 hours outside. In their rover, they covered 22 miles in total, with one drive taking the pair 4.7 miles from their spacecraft. The lunar roving vehicle, or moon buggy, was used to collect rocks. The 6 Apollo missions returned to Earth with 840 pounds of them. Analysis of these rocks revealed much about the history of the Moon. The oldest were about 4.6 billion years old, and their chemical composition clearly showed a common ancestry with rocks on Earth. Tests revealed no evidence of organic compounds, indicating that the Moon has always been a dry and lifeless world. Geologist-astronaut Harrison Schmitt collects samples from the lunar surface during the 1972 Apollo 17 mission. He spent many hours exploring the surface on the moon buggy. Lunokhod 1. The Soviet lunar program, which began in the early 1960s, relied on unmanned probes to explore the moon. 3 of the Soviet lunar probes returned with a total of 11.5 ounces of rock. Then, in November 1970, the Soviet lander Luna 17 arrived at a large lunar plain called the Sea of Rains. Luna 17 carried the remote-controlled rover Lunokhod 1. This was the first wheeled vehicle to traverse an extraterrestrial world, arriving about 8 months before the first Apollo buggy. The concept behind it was simple. Instead of sending moon rocks to Earth, the rover would do the analysis there. The Soviet Lunokhod 1 rover, seen here in tests on Earth, was the first rover ever to land on an alien world. Its predecessor, Lunokhod 0, was launched in 1969 but never reached orbit. Remote-controlled explorer. The Lunokhod rover was 7.5 ft long and resembled a motorized bathtub. The wheels were independently powered so that they could retain traction on the rough lunar terrain. Lunokhod was equipped with video cameras that sent back TV footage of the moon. An X-ray spectrometer was used to analyze the chemical composition of rocks, and a device called a penetrometer was pushed into the lunar regolith to measure its density. Lunokhod was powered by batteries that were charged by day using an array of solar panels that folded out from the top of the rover. At night, a source of radioactive polonium inside the machine acted as a heater to keep the machinery working. The rover received commands from controllers on Earth about where to go and when to perform experiments. A human might have done a better job, but rovers could stay in space for months on end and did not require food and water from Earth. Lunokhod 1 was designed to work for 3 months, but lasted almost 11. In January 1973, Lunokhod 2 landed in the Le Monnier crater on the edge of the Sea of Serenity. By June, Lunokhod 2 had traveled a total of 24 miles, a record that would stand for more than 3 decades. Over time you could terraform Mars to look like Earth. So it's a fixer-upper of a planet. Elon Musk, Canadian space entrepreneur. Martian walker. As Lunokhod 1 was exploring the moon, the Soviet space program was eyeing an even greater prize, a rover on Mars. In December 1971, 2 Soviet spacecraft, codenamed Mars 2 and Mars 3, sent modules to land on the Red Planet. Mars 2 crashed, but Mars 3 made a successful touchdown, the first ever landing on Mars. However, it lost all communications just 14.5 seconds later, probably due to damage from an intense dust storm. Scientists never found out what happened to Mars 3's cargo, a Prop M rover, a tiny 10 pounds vehicle designed to walk on 2 ski-shaped feet. It was powered through a 50-foot umbilical cord, and once on the surface was designed to take readings of the Martian soil. It is unlikely that the Prop M ever carried out its mission, but it was programmed to operate without input from Earth. A radio signal between the Moon and Earth travels in less than 2 seconds, but a signal to or from Mars takes between 3 and 21 minutes to arrive, varying with the planet's distance from Earth. For a Martian rover to be a successful explorer, it needed to work autonomously. Bounce down. In 1976, NASA's 2 Viking landers sent back the first pictures of Mars. Following this success, many more rovers were planned, but most of these projects never reached their destination, succumbing to what the press dubbed the Martian curse. NASA eventually had a success with its 1997 Mars Pathfinder mission. In July of that year, the Pathfinder spacecraft entered the Martian atmosphere. Slowed first by the friction of a heat shield and then by a large parachute, the spacecraft jettisoned its outer shielding, and the lander inside was lowered on a 65-foot tether. As it neared the surface, huge protective airbags inflated around the lander, and retrorockets on the spacecraft holding the tether fired to slow the speed of descent. The tether was then cut, and the lander bounced across the Martian surface until it rolled to a stop. Fortunately, once the airbags had deflated, the lander was the right side up. The 3 upper sides or petals of the tetrahedral lander folded outward, revealing the 24-pounds rover. During development, the rover was called MFX, short for Micro Rover Flight Experiment. However, it was known to the public as Sojourner, meaning traveler, and chosen for its link to Sojourner Truth, a 19th-century U.S. abolitionist and rights activist. We landed in a nice flat spot. Beautiful, really beautiful. Adam Steltzner, lead landing engineer, Curiosity. Rolling on Mars. Sojourner was the first rover to take a tour of the Martian surface. However, the Pathfinder mission was really a test for the innovative landing system and the technology that would power larger rovers in the future. The minuscule vehicle traveled just 300 feet during its 83-day mission, and never ventured farther than 40 feet from the lander. Now named the Carl Sagan Memorial Station, the lander was used to relay data from the rover back to Earth. Most of the rover's power came from small solar panels on the top. One of the goals of the mission was to see how these panels stood up to extreme temperatures, and what power could be generated in the faint Martian sunlight. The rover's activities were run from NASA's Jet Propulsion Laboratory in California, and JPL has remained the lead agency in developing Martian rovers. With the time delays inherent in communicating with Mars, it is not possible to drive a rover in real time, so every leg of a journey must be pre-programmed. To achieve this, cameras on the lander were used to create a virtual model of the surface around Sojourner. Human controllers could view the area in 3D from any angle before mapping a route for the rover. During its 83 days of operation, the tiny Sojourner rover explored around 2,691 square feet of the planet's surface and recorded 550 images. Spirit and Opportunity. Despite its limitations in terms of size and power, Sojourner's mission was a great success, and NASA pressed ahead with 2 Mars exploration rovers. In June 2003, Mare, named Spirit, and Mare B, Opportunity, were ready for launch. They were about the same size as a Lunokhod rover, but were much lighter, at around 400 pounds. By the end of January the following year, both were traveling across the Martian deserts, hills, and plains, photographing surface features and chemically analyzing rock samples and atmosphere. They sent back the most glorious vistas of the Martian landscape ever seen, enabling geologists to examine the large-scale structures of the planet. Spirit and Opportunity had landed using the same airbag and tether system as Sojourner. Like Sojourner, both relied on solar panels, but the new rovers were built as self-contained units, able to wander far from their landers. Each vehicle's 6 wheels were attached to a rocking mechanism, which made it possible for the rovers to keep at least 2 wheels on the ground as they crossed rugged terrain. The software offered a degree of autonomy so that the rovers could respond to unpredictable events, such as a sudden dust storm, without needing to wait for instructions from Earth. Whatever the reason you're on Mars is, I'm glad you're there. And I wish I was with you. Carl Sagan in a message for future explorers. Low expectations. Nevertheless, expectations for these rovers were low. JPL expected that they would cover about 2,000 feet and last for 90 Martian sols. During the Martian winter, however, the team did not know whether the solar-powered rovers would retain adequate power to keep working. Of all the solar system's rocky planets, the seasons of Mars are the most Earth-like, due to the similar tilts of the planet's rotational axis. Martian winters are dark and bitterly cold, with surface temperatures falling to as low as 225 degrees near the polar ice caps. As predicted, Martian winds blew fine dust onto the solar arrays, cutting their generating power, but the wind also blew the panels clean from time to time. As winter drew nearer, the JPL team searched for suitable locations in which the rovers could safely hibernate. To do this, they used a 3D viewer built from the images taken from the rover's stereoscopic cameras. They chose steep slopes that faced the rising sun in order to maximize electricity generation and to top off the batteries. All non-essential equipment was shut down so that power could be diverted to heaters that kept the rover's internal temperature above 40 degrees Fahrenheit. An artist's impression portrays a NASA Mars exploration rover. Rovers Opportunity and Spirit were launched a few weeks apart in 2003 and landed in January 2004 at two sites on Mars. Continuing mission. The hibernation worked, and incredibly, JPL has managed to extend the rover missions from a few days to several years. More than 5 years into its mission, however, Spirit became bogged down in soft soil. All attempts to free it by remote control from Earth failed, and unable to move to a winter refuge, Spirit finally lost power 10 months later. It had traveled 4.8 miles. Opportunity, meanwhile, has avoided mishap and continues to operate. In 2014, it beat Linocode 2's distance record, and by August 2015 it had completed the marathon distance of 26.4 miles. This was no mean feat on a planet located some hundreds of millions of miles from Earth. In the Kimberley Formation on Mars, photographed by Curiosity, strata indicate a flow of water. In the distance is Mount Sharp, named after U.S. geologist Robert P. Sharp in 2012. Curiosity needed. Spirit and Opportunity were equipped with the latest detectors, including a microscope for imaging mineral structures and a grinding tool for accessing samples from the interiors of rocks. However, Curiosity, the next rover to arrive on the planet in August 2012, carried instruments that not only studied the geology of Mars but also looked for biosignatures, the organic substances that would indicate whether Mars once harbored life. These included the SAM or Sample Analysis at Mars device, which vaporized samples of ground rock to reveal their chemicals. In addition, the rover monitored radiation levels to see whether the planet would be safe for future human colonization. Considerably larger than previous rovers, Curiosity was delivered to Mars in an unusual way. During the landing phase of the mission, the radio delay was 14 minutes, and the journey through the atmosphere to the surface would take just 7, all on autopilot. This created 7 minutes of terror. The engineers on Earth knew that by the time a signal arrived informing them that Curiosity had entered the Martian atmosphere, the rover would already have been on the ground for 7 minutes, and would be operational or smashed to pieces. The 7 minutes of terror has turned into the 7 minutes of triumph. John Grunsfeld, NASA Associate Administrator. Safe landing. As Curiosity's landing craft moved through the upper atmosphere, its heat shield glowed with heat, while rockets adjusted the descent speed to reach the Gale crater, an ancient crater caused by a massive meteorite impact. A parachute slowed the craft to about 200 miles per hour, but this was still too fast for a landing. It continued to slow its descent over a flat region of the crater, avoiding the 20,000-foot mountain at its center. The craft reached about 60 feet above the surface and then had to hover, since going too low would create a dust cloud that might wreck its instruments. The rover was finally delivered to the surface via a rocket-powered hovering platform called a sky crane. The sky crane then had to be detached and blasted clear of the area so that its eventual impact did not upset any future exploration. Having survived the landing, Curiosity signaled to Earth that it had arrived safely. Curiosity's power supply is expected to last at least 14 years, and the initial 2-year mission has now been extended indefinitely. So far, it has measured radiation levels, revealing that it may be possible for humans to survive on Mars, discovered an ancient stream bed, suggesting a past presence of water and perhaps even life, and found many of the key elements for life, including nitrogen, oxygen, hydrogen, and carbon. ExoMars. In 2020, the European Space Agency, in collaboration with the Russian Space Agency, Roscosmos, will launch its first Mars rover, ExoMars, with the goal of landing on Mars the following year. In addition to looking for signs of alien life, the solar-powered rover will carry a ground-penetrating radar that will look deep into Martian rocks to find groundwater. The ExoMars rover will communicate with Earth via the ExoMars Trace Gas Orbiter, which was launched in 2016. This system will limit data transfer to twice a day. The rover is designed to drive by itself. Its control software will build a virtual model of the terrain and navigate through that. The rover software was taught how to drive in Stevenage, England, at a mock-up of the Martian surface called the Mars Yard. The ExoMars rover is expected to operate for at least 7 months and to travel 2.5 miles across the Martian surface. It will be delivered to the surface by a robotic platform that will then remain in place to study the area around the landing site. See also, the space race exploring the solar system, understanding comets, studying Pluto. In context. Key development. European Extremely Large Telescope before 1610 Galileo Galilei makes the first recorded astronomical observations using a telescope. 1668 Isaac Newton makes the first usable reflecting telescope. 1946 Lyman Spitzer Jr. suggests putting telescopes in space to avoid Earth's atmospheric interference. 1990 The Hubble Space Telescope is launched. After 2015 construction begins in Chile on the US-led 72-foot giant Magellan telescope. 2016 LIGO detects the gravitational waves of objects in space. 2018 The James Webb Space Telescope will become the largest telescope ever launched into space. Despite its name, the ESO, or European Southern Observatory, is located in northern Chile, a region of dry desert and high mountains ideal for ground-based astronomy. This collaborative organization of 15 European countries, along with Brazil and Chile, has been pushing the limits of astronomy for more than 50 years. Big telescopes. The ESO uses literal names for its telescopes. In 1989, it began operating the New Technology Telescope, the new technology being adaptive optics that reduce the blurring effect on images caused by the turbulence of the atmosphere. In 1999, it opened its Very Large Telescope, which comprises 4 27-feet reflecting telescopes that can be used together. The Atacama Large Millimeter Array, a vast radio telescope with 66 antennae, then became operational in 2013. This is the largest ESO program to date, and the largest ground-based astronomical project of all time. In 2014, however, the ESO received funding for the European Extremely Large Telescope. When completed in 2024, this will be the largest optical telescope ever built, with a resolution 15 times sharper than the Hubble Space Telescope. The ELT's dome is shown opening as the sun sets over the desert in this artist's impression. The completed structure will be 256 feet high. Giant mirror. The ELT has an unusual 5-mirror design housed inside a dome half the size of a football stadium. The primary mirror, which collects the visible light, is built from 798 hexagonal segments that are 4 feet 10 inches wide. Together they will make a mirror that is 129 feet across. In contrast, the Hubble's primary mirror is just 7 feet 11 inches wide. Even the ELT's secondary mirror is larger than that, at 13 feet 10 inches. The shape of M1 can be fine-tuned to account for distortions caused by temperature changes, and by the gravitational effect as the telescope swings into different positions. M2 directs the light from M1 through a hole in the fourth mirror onto the third mirror. From there, light is reflected back onto M4, the adaptive optics mirror, which greatly reduces atmospheric blurring of the image. M4 follows the twinkling of an artificial star, which is created by firing a laser into the sky. M4 can alter its shape 1,000 times a second using 8,000 pistons housed underneath. In other words, the 798 segments of this astonishing mirror can ripple and warp in real time to counteract any atmospheric distortions. Finally, M5 directs the image into the camera. The ELT will pick up a narrower band of the spectrum than space telescopes, but it can do so on a much larger scale. As a result, the ELT will be able to see exoplanets, protoplanetary disks, black holes, and the first galaxies in greater detail than ever before. At the heart of the ELT's complex arrangement of mirrors is the huge dish of the primary mirror. It will gather 13 times more light than the largest existing optical telescopes, and will be aided by 6 laser guide star units. European Southern Observatory. Formed in 1962, the ESO today has 17 member countries: Austria, Belgium, the Czech Republic, Denmark, Finland, France, Germany, Italy, the Netherlands, Poland, Portugal, Spain, Sweden, Switzerland, and the UK, with Chile and Brazil. It is located in the Atacama Desert of Chile, chosen for its clear, moisture-free skies and the absence of light pollution. The ESO's headquarters is near Munich, Germany, but its working base is the Parinal Observatory, an ultra-modern science center in the remote desert. The observatory's subterranean living quarters were used as a Bond villain's lair in the 2008 movie Quantum of Solace. The site's new extremely large telescope is costing $1.1 billion to build. The ESO opted for this project after rejecting the far costlier OWL, overwhelmingly large telescope, the proposed design of which had a 330 feet wide primary mirror. See also Galileo's telescope, gravitational theory space telescopes studying distant stars. In context. Key organization LIGO. Before 1687, Isaac Newton formulates the universal law of gravitation, which sees gravity as a force between masses. 1915, Albert Einstein presents the general theory of relativity, which explains gravity as the distortion of spacetime by mass, predicting the existence of gravitational waves. 1960, American physicist Joseph Weber attempts to measure gravitational waves. 1984, Rai Weiss and Kip Thorne found LIGO. After 2034, ELISA is scheduled to search for gravitational waves using 3 spacecraft in heliocentric orbits, between which lasers will be fired. In 1916, as he worked on his theory of relativity, Albert Einstein predicted that, as a mass moved, its gravity would cause ripples in the fabric of spacetime. Every mass would do this, although larger masses would make bigger waves, in the same way that a pebble dropped in a pond makes an ever-increasing circle of ripples, while a meteor impacting the ocean creates tsunami-sized waves. In 2016, 100 years after Einstein's predictions, a collaboration between scientists working under the name LIGO announced that they had discovered these ripples, or gravitational waves. Their decades-long search had revealed the gravitational equivalent of tsunamis created by 2 black holes spiraling around each other, and then colliding. It is hoped that the discovery of gravitational waves will provide a new way of observing the universe. Instead of using light or other electromagnetic radiation, astronomers are hoping to map the universe by the gravitational effects of its contents. While radiation is obscured in many ways, including by the opaque plasma of the early universe up to 380,000 years after the Big Bang, gravitational waves pass through everything. This means that gravitational astronomy could see back to the very beginning of time, a trillionth of a second after the Big Bang. Within a period of 20 milliseconds, the two black holes LIGO had detected increased their orbital speed from 30 times a second to 250 times a second before colliding. Wave behaviors. LIGO stands for Laser Interferometer Gravitational Wave Observatory. It is a remarkable set of instruments for measuring expansions and contractions in space itself. This is no easy task. A ruler cannot do it because, as space changes in size, so does the ruler, so the observer measures no change at all. LIGO succeeded using the benchmark that remains constant whatever space is doing, the speed of light. Light behaves like a wave, but it does not require a medium through which to travel. Instead, light, and any kind of electromagnetic radiation, is an oscillation of an electromagnetic field. In other words, light is a disturbance in a field permeating all of space. Gravitational waves can be understood as disturbances in the gravitational field that permeates the universe. Einstein described how these disturbances are caused by the mass of objects curving the space around them. What is understood as the pull of gravity is a small mass appearing to alter its motion and fall toward a larger mass as it encounters a region of warped space. All masses are in motion, planets, stars, even galaxies, and as they move, they leave a trail of gravitational disturbances in their wake. Gravity waves propagate in a comparable way to sound waves, by distorting the medium through which they travel. In the case of sound waves, that medium is made of molecules, which are made to oscillate. In the case of gravity, the medium is spacetime, the very fabric of the universe. Einstein predicted that the speed of gravity would be the same as the speed of light, and that the ripples in spacetime would move outward in all directions. The intensity of these ripples diminishes rapidly with distance, so detecting a distinct gravity wave from a known object far out in space would require a very powerful source of waves and a very sensitive instrument. Laser-guided. As its name suggests, LIGO employs a technique called laser interferometry. This makes use of a property of waves called interference. When two waves meet, they interfere with one another to create a single wave. How they do this depends on their phase, the relative timing of their oscillations. If the waves are exactly in phase, rising and falling perfectly in sync, they will interfere constructively, merging to create a wave with double the intensity. By contrast, if the waves are exactly out of phase, one rising as the other falls, the interference will be destructive. The two waves will merge and cancel one another out, disappearing completely. LIGO's source of waves is a laser, which is a light beam that contains a single color, or wavelength, of light. In addition, the light in a laser beam is coherent, which means that its oscillations are all perfectly in time. Such beams can be made to interfere with one another in very precise ways. The laser beam is split in two and the resulting beams are sent off perpendicular to one another. They both hit a mirror and bounce straight back to the starting point. The distance traveled by each beam is very precisely controlled so that one has to travel exactly half a wavelength farther than the other. When the beams meet each other again, they are exactly out of phase as they interfere, and promptly disappear, unless a gravitational wave has passed through space while the beams were traveling. If present, a gravitational wave would stretch one of the laser tracks and compress the other, so the beams would end up traveling slightly altered distances. With no gravitational waves, LIGO's light waves cancel one another out when they are recombined. Gravitational waves stretch one tube while compressing the other, so that the waves are no longer perfectly aligned, and a signal is produced. Noise filter. The laser beams are split and sent on a 695-mile journey up and down LIGO's 2.5-mile-long arms before being recombined. This gives LIGO the sensitivity to detect minute perturbations in space that add up to a few thousandths of the width of a proton. With the distances put very slightly out of sync, the interfering beams would no longer cancel each other out. Instead, they would create a flickering pattern of light, perhaps indicating a gravity wave passing through LIGO's corner of space. The difficulty was that such a sensitive detector was prone to distortions from the frequent seismic waves that run through Earth's surface. To be sure that a laser flicker was not an Earth tremor, two identical detectors were built at opposite ends of the United States, one in Louisiana, the other in Washington state. Only signals registering on both detectors were gravitational waves. LIGO operated from 2002-2010 with no success, then started up again in 2015 with enhanced sensitivity. LIGO's precision instruments must be kept completely clean. Maintaining the purity of the laser beams is one of the project's biggest challenges. Colliding black holes. On September 14, 2015, at 9:50 and 45 seconds Greenwich Mean Time, two black holes a billion light-years away collided and unleashed huge warps in the fabric of space. In fact, this event occurred a billion years ago, but it had taken that long for the ripples they had released to reach Earth, where they were detected by both LIGO detectors. The researchers took another few months to check their result, and went public in February 2016. The search is now on for more gravitational waves, and the best place to do it is from space. In December 2015, the spacecraft LISA Pathfinder was launched. It is headed to an orbit at L1, which is a gravitationally stable position between the Sun and Earth. There, the spacecraft will test laser interferometry instruments in space, in the hope that they can be used in an ambitious experiment called LISA. Provisionally scheduled for 2034, LISA will use 3 spacecraft triangulated around the Sun. Lasers will be fired between the spacecraft, making a laser track 2 million miles long that is many times more sensitive to gravitational waves than LIGO. The discovery of gravitational waves has the potential to transform astronomers' view of the universe. The patterns and the fluctuations in the light signals from LIGO and future projects will produce new information, providing a detailed map of mass across the universe. Gravitational waves will bring us exquisitely accurate maps of black holes, maps of their spacetime. Kip Thorne. LIGO splits one beam of laser light and sends beams down 2 tubes at 90 degrees to each other. To prevent unwanted interference, the tubes are vacuums at 1/1,000,000th of the pressure of Earth's atmosphere. LIGO also has to make adjustments to allow for the tidal pull of the Sun and the Moon. Ry Weiss and Kip Thorne. LIGO is a collaboration between Caltech and MIT, and also shares its data with a similar experiment called Virgo, which is running in France and Poland. Hundreds of researchers have contributed to the discovery of gravitational waves. However, there are 2 people, both Americans, who stand out among them all: Rayner, Ry Weiss and Kip Thorne. In 1967, while at MIT, Weiss developed the laser interferometry technique used by LIGO, working from the initial ideas of Joseph Weber, one of the inventors of the laser. In 1984, Weiss co-founded LIGO with Thorne, a counterpart at Caltech, who is a leading expert on the theory of relativity. LIGO is the most expensive science project ever funded by the U.S. government, with a current cost of $1.1 billion. After 32 years of trying, in 2016 Weiss and Thorne announced their discovery of gravitational waves at a news conference in Washington, D.C. See also, Gravitational theory, the theory of relativity.